Good afternoon, class. We are looking at Chapter 4, Application of Derivatives, Section 4.6, Antiderivative. So we covered the max and mean, how derivatives affect the shape of a graph, optimization, and antiderivatives. So here's the differentiation formulas, linearization. We're going to discuss anti-differentiation. Integral calculus has two parts: differential calculus, which deals with instantaneous rate of change and slope of a tangent line, and integral calculus deals with accumulated change and area under a curve. Both parts rely heavily on the concept of a limit, and they are intimately related. Integral is the opposite of a derivative, also called antiderivative. The question is, given the derivative of a function, what is the original function? The antiderivative of f of x is the set of functions f of x plus c such that the derivative of capital F of x plus c is lowercase f of x. The constant c is called the constant of integration. When we differentiate, we get one answer, everyone. But when we integrate, we get a family of functions. That is the effect of a c, because the derivative of c, any number, any constant, is 0. Antidifferentiation is often called integration to indicate the antiderivative of x squared is x cubed over 3 plus c. We write the integral sign, the integral of x squared dx, is x cubed over 3, or 1/3 of x cubed plus c. The symbol elongated s was introduced by Leibniz and is called an integral sign. It is an elongated s and was chosen because an integral is a limit of sums. In general, the integral, there's the integral sign, of f of x dx is capital F of x plus c. F of x plus c is the general form of the antiderivative of lowercase f of x. Finally, if capital F and g are any two antiderivative of f, so therefore capital F prime equals f of x, capital G prime is f of x, then g and f must be the same with an exception of a c. That means one is the other one plus c. So g is f plus c. G of x equals f of x plus c. Let's do warm-up examples, and I want to make sure we understand. It's called indefinite integral because we have a constant. We are integrating 8. The purpose of the dx, everybody, is to know that we have the independent variable x. So the antiderivative, what do you differentiate to get 8? It's 8x. Therefore, 8x plus c. And to check it, you differentiate the right side and you get 8. Now, the importance of this is if I had 8 dt, then the answer would be 8t plus a constant. If I had 8 d theta, would be 8 theta plus a constant. So dx, dt, d theta, they tell us what is the independent variable. It is also known as a dummy variable because it is the concept that is important. Now, think about this. What is it that you take a derivative of to get 3x squared? Anybody? What is it that you differentiate and the result is 3x squared? X cubed. So it's x cubed plus c. And the proof is to differentiate the right side to see that it's 3x squared. Remember, when we were learning division first, we would check with the multiplication. So it's the same thing we are checking. Think about this. What do you differentiate to give you e to the power of x? Anybody? The answer is itself, e to the power of x and a constant. And if you differentiate the right side, you get e to the power of x. Finally, as a warm-up example, what do you differentiate to get 1 over x? That would be ln of absolute value of x plus a constant. The proof is by differentiating the right side. And why are we using an absolute value? Because, as you recall, the domain is 0 to infinity. So that's why we use an absolute value to be on the safe side. All right, let's look at some basic differentiation formulas. The derivative of kx is k, we know that, where k is a number, is a constant. Because of that, the reverse process, the integral of k dx, gives us kx plus c. Again, k is a constant. What about the derivative of x to the power of n, known as the power rule? The answer is 1 over n plus 1, x to the power of n plus 1, and a constant, n can't be negative 1. N can't be negative 1 because if it is, makes this denominator 0. So that's the power rule. The concept is very simple. When we want to differentiate x to the power of n, we know the answer is n x to the power of n minus 1. The process is to multiply by n and then subtract 1 from n, right? So we multiply by, so x to the power of n. We multiply the result, multiplication by n, and the exponent goes down by 1. Now, for the integration, we use the reverse process. The reverse process goes this way. So number 1, instead of subtracting 1, we are going to add 1 to n. And then instead of multiplying, we're going to divide by that, which is n plus 1. So first add 1 to n, then divide by n plus 1. So we're going to add, n becomes n plus 1, and we're going to divide by it. And we can also differentiate the right side to prove that. If you look at the derivative of this, dx of, let's write it as 1 over n plus 1, x to the power of n plus 1, and a constant. You see the answer is 1 over n plus 1 times, we're going to multiply it by n plus 1, and x to the power of n plus 1 minus 1 plus c will give us 0, and this is simply x to the power of n. So differentiate the right side, and you'll see the result. Power. Now the reverse process, the derivative of e to the power of x, e to the power of x. So the integral of e to the power of x is e to the power of x and a constant. Here's the natural log. The integral of 1 over x is the natural log and a constant. Here sine gives you cosine. The integral of cosine gives you sine. Now this one, because you have a negative sign, you're not going to say the integral of minus sine. You're going to say the integral of sine is minus cosine. That's the same concept, everybody. The derivative of tangent is secant squared. So the integral of secant squared is tan x. The derivative of cotangent is minus cosecant squared. So the integral of cosecant squared is minus cotangent. The integral of secant tan is secant. The integral of cosecant x cotangent x is minus cosecant. Constant multiple rule. Remember when we were differentiating, if a number was being multiplied, you keep it. So the same thing, you can keep it in or outside the integral sign. The sum and difference rules. The derivative of the sum was the sum of the derivatives. Now the integral of the sum is the sum of the integral. It works in the same manner. And in this case, when we want to differentiate e to the power of kx, we write the answer as itself and we multiply it by k. So what would be the reverse process? Divided by k. And again, if you have any doubts, differentiate the right side. You'll see the we are going to use the power rule here. So x to the power of 7. We are going to add 1 to 7. and we're going to divide by it. So we want to add 1 to 7 and divide by it. So 1 over 8, x to the power of 8. And of course, we add a constant. Okay, part B, using the power rule, what should be the answer, class? You add 1 to the exponent, and then you divide by it and a constant. So that becomes what? 100, right? So 1 over 100, x to the power of 100 plus a constant. When we were differentiating square root of x, we had to make a change, algebraic change, and we are going, in order to use the power rule, we're going to do the same thing. So now we can use the power rule. The exponent is 1/2. So we're going to add 1 to that, and we're going to divide by it. And of course, 1/2 and 1, they add up to 3/2. And 1 over 3/2 is 2/3. Again, just as we did with the differentiation, we changed this to x minus 3. Therefore, we could use the power rule. We are going to add 1 to negative 3, and then we're going to divide by it. And of course, a constant. Now, negative 3 and 1, this is negative 2, so is this one. So we're going to write this as 1 over negative 2, or simply minus 1/2 x to the power of minus 2 plus a constant. Take this down, make it x to the power of positive 2. That's your final answer. Notice, this is the only calculus step. Algebra, algebra, algebra. Calculus step is here. Only one calculus step. E to the power of 4x dx, we want to integrate that. And as I mentioned, in the case of a differentiation, we multiply by k. In the case of an integration, we divide. So we divide by 4. So 1 over 4, e to the power of 4x plus a constant. In this case, we divide by negative 3. So 1 over negative 3, or negative 1/3, e to the power of minus 3x and a constant. So we are dividing by k. We are dividing by k, everybody. Same thing here. And again, since some may be confused, we are going to rewrite this as e to the power of 1/2 x. So we know k is 1/2, everybody. And therefore, we are going to say 1 over 1/2 e to the power of 1/2 x and a constant. Now 1 over 1/2 is 2. And that's the final answer. Well, the integral of 1 over x dx is natural log of absolute value of x plus a constant. If you know x is positive, you don't have to put the absolute value. To make sure we understand what's going on, we are going to rewrite this as 2 times 1 over x. So we see this gives you the same answer as this one. So this gives you ln x. So 2 times ln x plus a constant. You don't have to rewrite it if you see it, but I just wanted to make sure it's clear to everybody. Again, I'm going to rewrite it as 1/2 times 1 over x. So we see again the derivative is a natural log, so we have a 1/2 in front. 1/2 ln of absolute value of x and a constant. Again, why are we doing this? So it becomes clear what we are dealing with. This is the function 1 over x. We are integrating. We want to integrate this, and again, we do it term by term, and we add them up accordingly. This one, 2 divided by 5, x to the power of 5. Plus this one, 3 over 4, x to the power of 4. This one, minus 7/3 x cubed. And I hope you recognize this one as exponent 1. So 1/2 x squared minus 5x and a constant, 1 by 1. For this one, the same as differentiation. First, we square it. And this one, 1/3 x cubed. This one minus a 10. Let me just write this. Minus 10 over 2 x to the power of 2, or minus 5x squared. Finally, plus 25x, and of course, a constant. So at the end, you just add the constant, everybody. Remember, when we wanted to differentiate, we did the same thing. We cut it into 3 pieces. 1, which is x, 2, which is minus 7 over x, and 3, which is 2 over x squared. So this is algebra. So again, algebraically, I'm going to rewrite this one as minus 7 times 1 over x, and this one as 2x to the power minus 2. The reason I do that, because I want you to notice, of course, 1 is x, and there's no question about that. This one is minus 7 times 1 over x, so minus 7 ln of x. Now this one, 2 divided by negative 2 plus 1, x to the power of negative 2 plus 1. The numerator is negative 1, so we get minus 2, x to the power of negative 1, which is minus 2 over x, and a constant. Okay, everyone? All right. Now, what about this one? First and foremost, notice it's dx here, but it's dt here, so stick with t. So instead of, so for 1, we have t not x, okay? So this is t, cosine. The derivative of cosine is negative sign, but the integral of cosine is positive sign, positive sign. So t plus sine t and a constant. T plus sine t and a constant. Again, please understand the difference between differentiation and integration. What did we do with the differentiation? We changed it so the power rule can be used. So x to the power of 1/3. X to the power of 1/3, we write it as 1 over 1/3 plus 1, x to the power of 1/3 plus 1. Now, minus sine x. Remember, the derivative of sine is cosine, but the integral of sine is negative cosine, but the integral of negative sine is positive cosine. So you can say minus, if you go with this one, minus negative cosine x, and of course a constant. So minus negative cosine x, because this minus is this one, and the derivative, the integral of sine is minus cosine. As you can see, this becomes 4/3. So this is 3/4. and this is 4/3. And 4/3, we can rewrite it if we want to go with the cube root as 3/4 a cube root of x to the power of 4 minus makes it plus cosine x and a constant. Again, this is the only calculus step. All of this is basic algebra. So if you kept it as x to the power of 4/3 is okay, but I'm changing it to the format that was given to us. Questions? All right. dp dt is 2e to the power of 3t, p of 0 equals 1. We are solving an initial value problem. So what is an initial value problem? Any equation containing a derivative is called a differential equation, or DE. A function which satisfies the equation is called a solution to the differential equation. An initial value problem is a differential equation along with a specified value of the unknown function called the initial condition. Meaning, class, you have been given a pair to help you find the constant. So for now, to see what's happening, let's ignore that. This means dp is 2e3t times dt. When you integrate both sides, this becomes p of t. And as you recall, differentiation we multiply by 3 and we write itself, but integration we divide by 3. So 2/3 e to the power of 3t plus a constant. Now, if this was missing, we would be done. End of this story. Now, what this does, it gives us the pair 0, 1, which helps us find the missing constant. So that means p of t equals this. So p, if you replace the t with 0, p of t, or the second coordinate, becomes 1. So p of 0 is 2/3 e to the power of 3 times 0 plus c equals 1. Now, this is all elementary algebra. As you know, this is e to the power of 0, which is 1. So 2/3 plus c is 1, and c becomes 1/3. You replace it here, and that's an initial value problem solved, meaning the constant is solved, because what you have here is a general solution, everybody. This is called general solution. Will be with the help of this pair, we have a specific solution, particular solution. Meaning, this is a family of functions. This is one function. Okay, very straightforward, everybody. Family of function versus one function. We want to find the initial value problem. dy dx is 1 over x plus 1 over square root of x. Y is 5, x is 1, which means the pair 1, 5. So first and foremost, we say dy is this times dx. And then if we integrate both sides, everybody, the left side becomes y. The right side, we're going to work on it. And to work on it, we are going to change this to x to the power of 1/2. Bring it up, make it to the power of negative 1/2. Now, this is easy. We know the answer is ln x, ln of absolute value of x. Plus this one, we use the power rule. 1 over negative 1/2 plus 1, x to the power of negative 1/2 plus 1, and don't forget the constant. Now this is 1/2. 1 over that becomes 2. This is 1/2, makes it x to the power of 1/2 or square root of x. So ln x plus 2 square root of x plus a constant. Again, this is our general solution. And if we didn't have this, we would be done. But we have the pair 1 comma 5. So we have the pair 1 comma 5. We plug in. We know ln 1 is 0. We know square root of 1 is 1. So 5 is 2 plus c. C becomes 3. And you plug in. This is a particular solution. Again, the meaning of that family of functions, one function with the help of one pair. With the help of one pair, we get to a family of functions. We get to a one function, a specific function. The initial value problem, we want to find f of x, where f of 2 is 1 and f prime is given as 3x squared plus 3x plus 7. So capital F of x is the integral of this times dx. That's a very simple integration, everybody. 3 divided by 3 makes it x cubed plus 3/2 x squared plus 7x and a constant. So it's very straightforward, just a power rule. So f of 2 equals 1. That means we have the pair 2 comma 1. Replace any x you see with 2, and the result capital F of x or y is 1. So 2 cubed plus 3/2, 2 squared plus 7 times 2 plus c must be 1. That's the meaning of it, everybody. So this is 8. And this one cancels out. This one is 3 times 2, 6. This is 14 and a constant. So they add up to 28. So subtract the 28 from 1 and you get negative 27. And here's the final answer. So what we are looking at are as follows. General solution and particular solution. So what it means is that if we didn't have this pair, we would be done here. And that's a family of functions. We do have a pair, we get a particular solution, and everybody's happy. By the way, you can always check plugin 2 must give you 1. Just the way we did the differentiation, if we have this one, we cut it into 2 fractions. And to do that, first we change this to x to the power 1/2. This is algebra. This is x to the power 1/2 itself because this has exponent 1. When the exponent is missing, class, the exponent is 1. So 1 minus 1/2 is 1/2. So this is x to the power 1/2. This is x to the power negative 1/2. So far, just pure algebra. Now, one step of calculus. According to the power rule, we're going to add 1 and then divide by it. So x to the power of 1/2 plus 1 divided by 1/2 plus 1. This one we got to add 1 and divide by it. So x to the power of negative 1/2 plus 1 divided by negative 1/2 plus 1 and a constant. So this one, add 1, divide by. This one, add 1, divide by. And don't forget the constant. Of course, 1/2 and 1 is 3/2. Negative 1/2 and 1 is 1/2. Now, again, let me just do this so everybody can see. This is the calculus part and you're done. Everything else is algebra. So was this one. So was this one. So one step of calculus. So x to the power of 3/2 plus x to the power of 1/2 over 1/2 and so forth. And the only thing is we don't want to have a complex fraction. So when you divide by 3/2, that means times 2/3. When you divide by 1/2, that means times 2. So again, algebra. I hope everybody is comfortable with this concept. It is very straightforward, everybody. A sample of cesium-137 with an initial mass of 79 milligrams decays 2 years later at a rate of negative 1.8249 e to the power of negative 0.0231 milligrams per year. Find the mass of the sample after 23 years and 1 decimal. By the way, when they ask you to do the rounding takes place at the very last moment, not any of the intermediate steps. So let m of t represent the mass of cesium-137 after t years. What is given is m prime of t, or dm dt is this formula. dm dt is this formula, with the initial mass m of 0 being 79. So we find m of t and then m of 23. So this is the translation of the question. Excuse me. One more time. Here's the rate, dm dt. Initial value, m of 0 is 79. Find the mass after 23 years. So we're going to find m of t in general. And then specifically m of 23. So if dm dt is this, you put the dt on this side, the integral of dm gives you m of t and the integral of the right side. So again, this times dt, I can't emphasize this enough. If you want, you can write this intermediate step of. So you have to write dm equals negative 1.8249 e to the power of minus 0.0231 t, and then you have to take the integral of both sides. I forgot to write the dt here, my apologies. And so m of t is this. It's very straightforward. When you differentiate exponentials, you divide by this number, you multiply by this number. Because we are integrating, we are dividing by this number. So the answer is itself the same thing. Now we are going to divide the coefficient negative 1.8249 by the coefficient of t. Remember, with differentiation, we would multiply. And a constant. So again, this number, it just remains. And you divide by this number. Look at this one. The integral of e to the power of kx dx is 1 over k, e to the power of kx plus a constant. Therefore, m of t is this. Now use a calculator. Negative over negative is positive. You use a calculator and it becomes 79. So this is m of t. That's a general solution. But we have m of 0 equals 79. This is a family of functions. With the help of that, we can find c. So if you replace the t with 0, okay, you get 79 e to the power of 0 plus a constant is 79. As you know, this is 1, so 79 plus c is 79, makes it 0, c0. Therefore, here's your function, m of t, 79 e to the power of negative 0.020, negative 0.0231 t. That's your function. When do we need it for? After 23 years. We want it after 23 years. So plug in 23. Plug in 23 and evaluate it. Now at this point, you just have to use a calculator, everybody. Using a calculator, meaning multiply these two numbers, raise e to that power times 79, this is the answer. And now we go with 1 decimal, 4, next to it is 3, it doesn't change. Again, intermediate steps, I have kept all the as many decimals as possible, and now you do the rounding. I can't emphasize this enough, class, otherwise it will become wrong, okay? So the intermediate steps must be kept with many decimals. Quickly, this is reminding you of the antiderivatives, okay? Cf of x, so c remains. If you are looking at the sum, capital F plus g, x to the power of n is power of n plus 1 over n plus 1, 1 over x is ln x, e to the power of x is itself, cosine gives you sine, sine gives you minus cosine. So these are particular antiderivative, meaning you have to consider the constant. Secant squared is tan x, secant x is tan x, and that's good enough for us here.